a star that's so big, do you think it could be accreting material without actually having any magnetic fields? And there is research that backs up that massive stars don't have magnetic fields, so you don't actually need them to be doing, what the star needs to be doing. And so there's a lot of checks and balances that need to happen at the same time. It's not just, the graphs that I showed you. There's so much thinking about whether the science makes sense or not that goes into it. And this is where publishing papers really help, because then it goes to reviewers and it's not just biased by your thinking. There are people who are, providing you feedback saying, oh, have you thought about this aspect? Have you run this kind of models? What are your, thoughts about if you were to change this? So that actually challenges your thinking a lot. And this sometimes, it takes up to a year to actually, get back to those questions to the reviewers with answers and making sure that what you are presenting actually is solid. And so there's a lot of work that is behind just not looking at data and actually just thinking and that, truly of a scientist to think about what you're doing, if that is scientifically accurate.
Hello and welcome to a new episode on Hyperbolic Orbits podcast. I'm back after a much needed break, and to kick off this lovely season of many more nice conversations with space professionals, we have today a bona fide space scientist who is also one of the most warm and one of the most loved science communicators of our times. We have with us today Dr. Parshati Patel, who is an astrophysicist turned science communicator. She's a space industry professional, author, artist, and an astrophotographer based in London, Ontario, Canada. She holds a BSc with honors in physics and astronomy from the University of Toronto and MSc and PhD in astronomy and planetary science and exploration from Western University. For over 13 years, she has dedicated her career to inspiring curiosity about space among diverse audiences, especially youth and educators. Parshati has spearheaded award-winning space outreach initiatives and organized hundreds of public engagement events and workshops. Recently, she has also received the King Charles III Coronation Medal for STEM engagement. A highly sought-after speaker, she frequently contributes to local, national, and international media outlets in English, Hindi, and Gujarati. She is the author of the children's book, My Book of Stars and Planets with TK Publishing, and serves on the board of advisors for Students for the Exploration and Development of Space Canada, which we know as SEDS, and Zenith Canada Pathways. And she is also on the board of directors for the Royal Canadian Institute of Science. Thank you so much, Dr. Patel, for joining us today.
Thank you for having me. I'm really excited about this conversation.
Me too. So let's begin. The first question is always, I'd like to know how your journey in space started. How was it for you?
Yeah, so I'm originally from Ahmedabad. I was born and brought up there, and my first kind of inkling, I was always a curious student. I always loved reading books and learning about different things. Wasn't in particular science to start with. I remember having everything from history books to dictionaries, everything, just learn about everything around us. But I think the spark of space really started when I remember visiting Mumbai as a family, touristy thing that you'd go from Ahmedabad. And my first interaction with space was at the planetarium. And so that was the first time I knew there was something beyond the moon and the stars. And I'd never actually thought deeply about them until I visited the planetarium. And that just started this exploration of what's out there? What are these stars? And oh, there are more stars than our sun that are like our sun, but there are also different ones. And I think I asked too many questions after my trip to my parents that they were like, we don't know. My mom has a biology background. My dad has a business background. They would get me books. because that was their way of like, okay, here, learn more about whatever questions you have. And this was pre-internet era in a way that, you know, books were the only way of consuming, you know, your knowledge and like, you know, kind of find ways to garner your like, you know, curiosity. So that was really my kickstarting point into space. And what ended up happening was when people would ask, you know, when it's your birthday, people want to get you gifts, or someone is coming from abroad, you know, they want to get you gifts. They asked my parents, what Parshati like? And so they would say, oh, anything about the space thing. They say she seems to be liking that a lot. So I remember distinctly, you know, people giving me books, but I think one distinct gift that kind of changed the trajectory was really a gift of a telescope. So my aunt, who, you know, who lived here in Canada, she came with a small telescope. It wasn't really big, but big enough to be able to see the moon, you know, Saturn, Jupiter, Mars. And the first time I remember setting it up on my terrace and, you know, just trying to like struggle on how to do this. And then the moment I got it, I was just like, wow, I could do this for a living. Like this would be so exciting to just look at the moon, look at the planets, and just like wonder what is on the surface, what is going on in these planetary bodies. And I just thought, oh, that would be so cool to like be able to study these. And then that really started like this exploration of different questions I had about the universe. And it was very interesting that I connected a lot with planets and stars more than like galaxies and cosmology, just because I felt like thanks to my telescope and then onwards to, you know, joining different astronomy groups, etc., that I could see myself, you know, being able to be an observational astronomer, and it'd be more tangible. So really, I decided that, you know, in high school that I wanted to study astronomy. And, you know, I pursued my parents a lot once I started my college in India in BSc physics, that I really want to go abroad and, you know, study, you know, go to like a PhD level research. So I ended up, you know, thankfully coming to Canada, doing my undergraduate, master's and PhD, and it just became a journey.
And I think the kind of motivation or the kind of passion you had as a child, it's still there. When I see your work on social media, it's so real and it's like organically coming from you. I think that's what makes all of it so beautiful. But you know, it's nice to get motivated by looking at the telescopes, planetarium. They're all it's one of the most imaginative and the most daring thing a child could get inspired by. And then when you start studying even a bit of science and maths in high school, and then you realize, okay, what I'm getting into is actually quite intense and I cannot give up. So what was that point for you, and how did you decide, okay, I'll still go for astrophysics, knowing that I'm going to have to do some very crazy, challenging stuff?
Yeah, so I would say, you know, flat out, I was never a straight A student or anything. You know, I was a curious child, but like I didn't like, you know, I wasn't part of top 10. I probably wasn't even part of top 20 or top 30 in the class either, right? Like class of 60, 70 people. I wasn't, you know, on there that, you know, I would excel at physics and math. What I was really good at was asking questions. Like I was always curious. I wanted to like know more. I wanted to say, how do I do things differently, or how do I understand something that someone is explaining in one way, but it's not setting with me? Okay, how can I find another way to kind of understand the same thing? And I found physics really hard. Like in high school, I did question myself whether or not I will be able to study astronomy. And this was one of the reasons why I said, you know, I'll take into BSc physics and see how I feel about the subject. And even in my undergrad, when I did end up getting into undergrad, I did have, like, I was doing astronomy, which is what I've always wanted. But then I realized, like, what if I don't score good? What if, like, I don't get into masters, you know? So then I was like, oh, then I should also do BSc physics, because that will likely get me a job. You know, I always, until I got into my masters, at the end of my masters, I would say I always had a backup plan, because I never was confident about my skills. I think it was very much about, I was passionate. I was like, you know, trying to find ways to make it, you know, to the place I wanted to be, which was a PhD, doing my own research on a topic that I liked. And I will share one incident, which I think really kept my passion. Like I realized that if I wanted to pursue something, I had to find my own ways. And this was in my at the end of my second year in my bachelor's. This was in bachelor's of physics and astronomy at University of Toronto. I was taking this astronomy course. It was really hard, and the only way people were, passing the course was working together. And because I just moved to Canada, I was very much like a shy person. I didn't have any friends. I was by myself trying to work things out, and I wasn't scoring well. And after I wrote my final exam, I knew that I'm not going to pass. I'm like, this is the course I'm going to fail. And this is the first course I was ever going to fail. And it just meant that I will have to, pay the fees again for, having to take the course, which, as an international student, is really high. And then not only that, how am I going to do this next year? Because the professors wasn't providing answers. So how do I know where I went wrong or what I could have done better? And so I realized over the next, summer months, I was like strategizing, what can I do to make sure that this doesn't happen again? And so I dropped the course. You're allowed to actually drop one course during your entire degree. And I said, it's only second year, but this is the course that's going to be the one. And I realized that most of the people passed because they had friends and they could talk to them and figure out, and you could work in pairs or in groups and, submit an assignment like that. And so I decided to actually contact a person, who was in my group. And I said, hey, would you be able to help me with this course? And I not only passed that course, I actually got an A on that course, which I had never gotten an A. And so this was my turning point. I decided that if there are things not working out, I need to find other ways. And I have to get outside my comfort zone of talking to people, making sure that, I'm finding ways so that I can, pass the courses, learn what I need to learn to go on to the next step. And so it's never easy. It is maths and physics are probably the most scariest subjects you can take, anytime, whether it's high school or an undergrad or grad school. But it's really just finding the way you learn and how others can help you to do that.
I think group studies is one of the best experiences you can have at university. It's like people of the same age, they're coming together, trying to do the same hard things that you're trying to do and somehow figuring things out. Thank you. Now, I'll actually take a jump right from that to one of our most recent, loved and celebrated groups of the recent years, which is our Artemis II crew. Canada had a huge role to play in that mission, thanks to astronaut Jeremy Hansen. And I would like to know from you, because you are active, you are in that space, you know how it is, how that mission has inspired so many other people to think about space in a very different way. So I'd like to know what has been the after effects of Artemis II in Canada.
Yeah, wow, there is so much love for Jeremy and the space, Canadian space field in general. I think it was a historic moment and they chose the right person for doing it. He had been waiting for an assignment for so long. And everywhere, I go, I talk to people. I think one of the main factors that people particularly kind of gravitated towards this crew was not only their friendship within themselves, but it was also that 24/7 coverage that we had, which, a reality show kind of aspect to it, which helped us to kind of see what astronauts do on a daily basis, right? It is a job, but also at the same time, these are people who are excited about space, excited about the things that they get to do, and we got to see them do that, get excited about it. And I think that really came down to people here. And so everyone I talk to, they have their favorite moments from that entire, mission, whether it's launch, whether it's, them being able to see the solar eclipse or the surface of the moon. And different people have different connections to the particular moment. I just gave a talk last week about Artemis II, and it was really interesting on the kinds of things that resonated with people. Some people said they were really excited that Canada got to do this. Others were like, oh, that amazing picture of Earth from the moon, like full Earth with the auroras on both ends, the North and the South Pole, which you don't really get to see from pictures that you get from ISS. And so it's really different. For me, I think it's very hard to pick one thing. It was the entire mission. There are so many nuggets in there. But it's really that the way it brought Canadians together. I think that moment you can always see if I'm wearing something and people see, moon related, but be like, oh, Artemis II. A couple of weeks ago, I had my art booth, and most of my paintings were like, space related, with a couple of them inspired from Artemis II. And someone's like, oh, you're already on Artemis II. Wow. Like, you already caught up on painting that, right? So it's like people walking by and like recognizing Artemis II, just even in pictures, this is a painting. It's not even a picture of that, but with pictures and with Jeremy and with like just anything space related, it has resonated so much with Canadians.
I know a lot of engineers, and that includes me, that robotic exploration is much needed. Of course, it is needed. But what human spaceflight can do is beyond the tangible things of space exploration. And you rightly said, the live coverage. I think it's one of the first times that we clearly got to see that scientists, educators, journalists, engineers, they're all together, especially when mission control was being run by a scientist. Capcom, that was an amazing moment. And that brings me to my next question, actually, is that a lot of times I've been trying to try to explain this to a lot of people. In the Indian Space Research Organization, even I think now, a lot of engineers get the designation of a scientist. So it's very common in all of India to consider anyone who works in space to be a scientist. And in Artemis II, I think they brought out, all the communication was also very clear. They were talking about testing systems. Even Artemis III just announced that they are going to test docking, which is one of the most critical things to do before you even try to land. So do you think people are understanding that everyone is welcome? You do not have to be, rocket science is kind of a very strange field that nobody really knew what it entailed. And suddenly you're seeing everyone coming together. How do you see that happening right now?
Yeah, I think you gave a perfect example. The mission control room was filled with people from so many different experiences. You had communicators, who were journalists, like you said. There were scientists which I think if I were to pick a moment, that was my moment of having a scientist on the comms panel. And, astronauts. Well, Dr. Jenny Gibbons, who's also a Canadian astronaut, she was also part of the Capcom. She has a background in combustion science. She's an engineer as well. But then you had people who were measuring and maintaining, the orientation of the spacecraft and all of those technical bits as well as science bits. And then you have communications bits. You had things like the zero gravity indicator. To me, that is a part of art of the science that you do, right? And that also resonated a lot with people. So, I would say the STEAM aspect were completely represented within that Capcom. And so I think a lot of people do understand that there are different things that you do now, thanks to this 24/7 coverage and, awesome work done by the media to kind of cover all aspects of the mission. And I think so far what I've been doing and I want to continue to do is really talk about the science, because my background is really trying to understand. I have a minor in planetary science, which also got me to trying to understand the surface of the moon. So for me, that was really exciting. And different people have different things that resonate with them. So one thing, when I was talking to the cohort of the space enthusiasts that I thought would have known everything and anything about the mission, but maybe I was way too addicted with it, because I gave this 1 hour talk and I talked about all these different science that was happening, and not a lot of people knew about that. So people knew about the mission, they knew about Jeremy was born in London, Ontario. Like, he's very well known here. And they knew about the mission, but they didn't know a lot about the details. So I think one of the things that, I want to kind of continue doing is to bring highlight to the amount of science that these astronauts do. It's part of their job. People are aware of some of the things, but not everything. And so I think it is really on to science communicators like me and others to really bring that out.
And from that, now I really want to go to your specialization. Right now, I'll be your only audience. So the only question you will get is from me. And if anyone watching who has questions based on what Dr. Patel is going to teach us right now, please feel free to write down in the comments and we'll try to get back to you.
So today I'll share a little bit more about the research that I did in my PhD and why I'm so always excited about the stars. And I think I mentioned this earlier, that I was always gravitated towards stars and planets. And ever since, I got to see them through my own telescope, I've always been fascinated. How are they formed? What is needed for them to form? And so I remember calling myself for quite a long time detective, because before my passion for space, I really wanted to be police detective, because I thought I had the curiosity and observational skills to be able to solve crimes. And so I kind of brought that thread to me solving mysteries in the universe. So I still call myself a stellar detective. I don't do astronomy research anymore. I've moved on to the field in industry. And before this, academia, but I still call myself stellar detective. And so today I'll share a little bit about what drew me into the research that I did, because in PhD, I got to pick what I wanted to do, and I selected these particular kinds of stars that are really interesting. But before we move on to that, we'll look at a little bit about what it is about those kinds of stars and leading up to that really interests me. So here's an image of stellar nurseries. So these are the regions where stars are born. They have the right amount of material, dust and gas, the winds, that really becomes the right place for these kinds of objects to form. What you're seeing here are two different, star forming regions. On the left side, we have a nebula where it's a constellation of Cygnus. If you have had a chance to look at different constellations in the night sky, this particular region is 2,000 light years away, and it's an isolated area in Milky Way, but you can see the stars forming in that region. And what's really exciting is how 3D it looks in the image, even though the image is a 2D. For me, my favorite place to actually study is the Orion Nebula, which is here on the right-hand side. And that region, if you are able to see the Orion constellation and you have binoculars, you should be able to see, spot the Orion Nebula with your binoculars. I really particularly love this region because not only, it's a fantastic looking star forming region, but it also has something that was of interest to me, which was young stars that were very nicely imaged by the Hubble Space Telescope. So here is an image. So this is the same region on the left that I showed you before, but now with the small images of these stars that are young, that are forming, that was taken by Hubble. And what's really interesting is that these were taken in 1990, so they're pretty old in astronomical field scale, but you can see there's a huge variety. Some of them have, they're being blown away by the wind, and you can see that some have disks, and some have, stars, basically the central star peaking from it. You have regions that are being eroded by the wind, forming this long tails. So there's a huge variety of these young stars in these star forming regions. And I picked Orion particularly because it has images that we're visibly able to see these stars. And what's really interesting about these regions is that we find star forming regions everywhere. Our sun, basically all stars are formed in these regions. They have, other stars that may or may not look like them. So before I jump into the kinds of stars I study, I'll give you a little bit of an idea of what kinds of stars can we find. So if you look around the night sky, if you were to go out, in a dark sky area, and if you were to look around, there are thousands of stars in the night sky. And if you were to pick them and put them in, let's say, bins of what they look like, this is kind of what we'll get. Obviously, this is not how we bin the stars, but this is a great visualization of what it would look like in terms of the masses of these stars. So if we start from left to right, you have the smallest size, the redder star M, and it goes all the way to O. There's a very interesting story behind the naming convention, which I'll not get into right now. But what's really important is that they come in a lot of different sizes and also a lot of different temperatures, which, dictates the color that we see. So we know our sun is a G-type star, yellowish on this scale. What I was really interested in studying massive stars. So these are B-type stars, and so they are not the biggest, but a little bit, just off the scale from the biggest one. The stars itself, their surface temperature can raise anywhere from 30 to 3,000 to 30,000 degrees. And their masses can go anywhere from 0.1 to 60 times the mass of the sun. The ones that I was interested were the B-type stars, where their surface is anywhere between 10 to 20 times that of the sun. And one really interesting thing about the massive stars, so the ones on the massive spectrum, is the fact that their lifetimes are shorter. So the more massive you are, the faster use of the fuel, the faster you die. And this is in astronomical time scales. So when I mean by fast, it isn't really super fast in human terms, but in sun term or star terms, it's really fast. And so what I was interested was really actually studying how these stars are forming. And the reason why I came across massive stars was really my master's research. I didn't really know much about massive stars other than what, I really took kind of courses, what we get in textbooks. When I started my master's research, I started to understand that these massive stars are in some ways really violent. They're really high speeds, they churn out material from their equator just because they spin so fast. They're really high temperature, and they're just very exciting. I don't know, compared to our sun, at least I thought so. And so what I wanted to really understand is how these kinds of stars actually form. And what's really interesting is that when these stars are forming, they actually have a thick wall of dust and gas around them. And so it's really hard to see what is happening. And if you may have guessed in a lot of my previous slides, is that I love visualizing what is happening. I'm a visual learner. I love to draw and put down, things that I'm able to envision. And in this particular case of stars, as they're forming, the more massive they are because they're forming so much more faster, and there's still dust and gas from that star forming region that's still around them. And so we're not really able to see what is happening. And I really wanted to try to understand what is happening behind those dark wall of dust and gas. And so this was really my main focus of my PhD, is finding these B-type stars and trying to understand how they're forming. So if I were to take a slice of what you're seeing on the screen right now, this is what it would look like. So you would have a star that's forming in the middle. Obviously, this is not really to the scale. And then you have, a little bit of a space between the two. Now, what is happening between that space was really controversial in terms of people didn't know. And then as you go further away from the star, you're starting to see more dust, and then eventually this is where the planets would form if planets were to form in that system. And so I really wanted to understand that gap. Is there a gap between where the dust starts to form and where the gas exists and the surface of the star? And so the way I did this is I actually had an opportunity doing PhD here in Canada that I had access to some of the telescopes. Here's an example, the Canada France Hawaii telescope. I got some observation time on the telescope, and I was able to collect data. And then my research group actually had a computational model. So I combined my observations that I took from the telescope with a computational model. This is where you actually take all the physics and math that you have learned and you build a star and a disk around it. So the image that you're seeing on the screen is actually a computationally generated image of what the star and the disk looks like in this computer generated coding that we do. And what we really wanted to do was to take what we had in terms of observations and see if we were able to match with the thickness of the disk, the kind of the disk, the movement of the disk, etc. And the way we do it is we really use the light that's the only thing we're getting from these stars. So I'll show you an example of what a spectrum of one of the stars that I was studying looked like. So here's the spectra of a star. So, we looked at the visible and near infrared, and I highlighted some of the key, features in the spectra. So we're looking at the two red ones are the hydrogen lines that we're seeing. And then I also had calcium and some other lines as well, iron, as well as helium as well, which I haven't highlighted here. But these were what were interesting to me because these elements are present in the disk around the star, and they can tell me what is going on. And so I would then go to my computational model and, figure out what I think might be the disk size, the thickness, what the material would be, and see if I'm able to reproduce these lines. And so I'll just give you an example of I had tons and tons of different observations of this particular star. So I'll show you one example of what my computational model versus what my actual observed model or my observations were able to match. So here is an example. So you can see the red is what I generated from the computational model, while blue is what we observed. And so we were able to, I wouldn't say 100%, but almost there in terms of being able to match the observations. So, I knew the disk was thin. I knew that it was mostly gaseous disk, the speed at which it was moving, where were these elements present. And so this is a really a very shortened version of what my PhD looked like. But I think what I'm able to really share with you is that you can go from just wanting to study something and then come up with your own idea. This is why I wanted to really do a PhD, because I could come up with my own idea, be able to, formulate the thesis, what it would look like, do the observations, do, the computational modeling, compare the data, analyze the results, and publish, which is what we scientists always like to do. But I hope I was able to give you a very tiny insight into what my PhD looks like. It was 4 years combined, pretty much stressed into the 10 minutes that I shared with you. But I'm happy to take questions in the comments. I'll try and answer as much as possible. Thank you.
Thanks a lot. I mean, it's an incredible job that you did. You put together 4 years of that to PhD level studies into a presentation in 10 minutes. That itself deserves a huge round of applause. So thank you. And, whenever we see such presentations from scientists, there are always two common questions. First is, how do we measure the mass of such distant stars sitting on Earth? What kind of instruments we use? And another one, which is maybe not so common, but my interest is, what kind of computational models did you use and how did you do the simulations?
Yeah, great question. So the first one we use, so in terms of tools, really depends on what you're trying to study. So because I really wanted to study the light that was coming up, I knew I wanted to use a spectrometer, on different telescopes, and CFHT was just one of the examples that I gave. I had access to some other telescopes and archival data, which, a lot of people, forget that there is tons of free archival data that you can actually find that is really useful for your research. You don't always have to go to observational. And then in terms of calculating a lot of the content of like what the star mass might be, what could the temperature be, all of those, a lot of people have spent their entire lives just doing that. So they use lots of different tools. This could be, looking at similar, light, from the star spectrum. But then also other features, a lot of these stars are binary. So you're able to actually measure a lot of the elements from the binary systems. So there are lots of people who have spent. And so I basically used a lot of research that was already done. So I looked up archival, papers about these stars, what they're saying about the mass, and that included that in my models. So, I can basically say whether or not if I'm able to match these spectra with the observational, whether or not that's actually accurate. So that's another way to actually confirm the numbers that people have already published, is using our computational model. So that actually, brings us to your second question. In terms of computational model, so I was really lucky that for my master's, I actually joined a group that already had these models built, which was one of the reasons why I came up with this idea of my PhD, that, hey, I wanted to study these stars. None of my group members were actually studying young stars. These particular models were actually built for, what we call a main sequence star. So something like our sun, that is steadily, burning its fuel. What I wanted to study was young stars. So I kind of merged my two interests together. And these models really are based on the physics. So the physics of the stars, the physics of the light, how light reflects from these elements that you're seeing around the star. How do disks actually form? What is the physics of the disk? And how would, you being an observer so far away from the star, how would that light change between you and the star? So there's so much physics that goes into it. And it was probably a decade or more of my supervisor and his team to be building these models for me to then be able to come in and do this research. So I would really say I was the operator of these computational models rather than the developer of it. And I think this is why I was able to finish my PhD in 4 years, is because I really had the data and I could operate and get the data to actually compare it.
When you, let's say, have so much data in front of you, seeing that something has happened, this is what is happening, how do you combine that understanding with a kind of communication that is also a very important part of PhD thesis?
Yeah, so I think I did, and this, I remember saying this during my thesis, is like, yeah, I ran over like 6,000 models at some point in the, and I'm probably sure like I did more, but I think those were the ones that I was actually ended up using. So, there's a lot of work that goes into figuring out what are the knobs. This is like, I think of this as, being a pilot, and the amount of knobs that you have in front of your screen, there's so much that I could change that would change the end result. And so I needed, this validation of like making sure that my masses were correct, the physics that's in there is correct. And then, out of all of these models, which are the ones that actually fit the best? This is where the statistics comes in, right? Statistically, which one is the best that matches to the observational data? And then once you have that, you really need to think about, what is this computational model telling me? Does this even physically make sense for, let's say, a star that's so big? And do you think it could be accreting material without actually having any magnetic fields? And there is research that backs up that massive stars don't have magnetic fields, so you don't actually need them to be doing, what the star needs to be doing. And so there's a lot of checks and balances that need to happen at the same time. It's not just, the graphs that I showed you. There's so much thinking about whether the science makes sense or not that goes into it. And this is where publishing papers really help, because then it goes to reviewers and it's not just biased by your thinking. There are people who are, providing you feedback, saying, oh, have you thought about this aspect? Have you run this kind of models? What are your, thoughts about if you were to change this? So that actually challenges your thinking a lot. And this sometimes, it takes up to a year to actually, get back to those answers, questions to the reviewers with answers, and making sure that what you are presenting actually is solid. And so there's a lot of work that is behind just not looking at data and actually just thinking and that, truly of a scientist to think about what you're doing, if that is scientifically accurate.
Lovely. And then from stellar physics, then when something like Artemis happens, you have got to explain the science behind moon missions. So, how do you go about jumping from there to this? I mean, it's well within your abilities and skills, but knowing something and communicating things are two different. So, how do you balance that out, and how has been the Artemis communication experience for you?
Yeah, so for me, I think it all began in my PhD, and it didn't start as, something I wanted to do or something that I thought I could do. It really started off. So I think I mentioned earlier in our conversation that, I was a shy person. I hardly would make friends. One of the other things I always thought in the start years of, when I moved here was that I don't think people understand my language, like, the accent that I'm speaking with, or the other way around. I thought I couldn't really understand if they were speaking too fast. So I actually took up my first ever like volunteer job was to edit. There used to be a radio show at that time, which was about planetary science. It ended up being a podcast at one point. And I started off editing because I thought that would help me with my listening skills. And that turned into a job, a paid position to run the entire show. And that just trusted me into science communication without actually knowing what science communication was. I ended up going to schools, and at that time I had to talk about planetary science because my minor was in planetary science, and the center, which is now an institute, used to be about planetary science and exploration. And so they were really wanting to bring people from different aspects of, not only STEM, but now they also include people from like law, psychology, etc., into their group. And so I really got that exposure of like not only astronomy, but here's what engineers do, here is what scientists do on mission, and how they'll work together. And so that brought out how to do science communication. And so I think I just observed people doing it so well. I took that on to me. And so when I graduated, I think the 4 years of doing this kind of gave me a lot of skills. And I ended up actually making a career out of it. I ended up, leading education outreach at the same institute for 4 years. Ended up working at the space agency, in their youth education program, and a little bit ended up also, doing a few contracts as a scientist as well there. But really, all that different exposure really gave me that, knowledge base that I needed to be able to understand different aspects. And when I don't, I now have like a huge group of friends who were part of that program that are from that diverse field that I can ping and be like, I have a friend who is a lunar geologist. And I'll be like, the other day I asked a question, I said, oh, they were asking me about lava tubes on the, the far side. Are there any? I don't know. Like they asked me this question, I did not know. And so I have these people that I can actually ask questions and then be able to improve my understanding of like what I'm trying to explain. So it really is a skill that you develop over time, and it really gets better with practice. And so, I used to be afraid of public speaking or speaking in front of like even my classmates, and to now doing talks and all the time. And so it really is that excitement that I want to communicate about what I'm passionate about. And then B, really people, if they're looking for it, they will ask you questions. And so being able to do that, you really need to have observational and listening skills, being able to understand the science behind things as well. So it's a lot of that compound experience kind of led me to what I'm doing today.
I loved you said that. Recently, I think we don't talk about this enough. Space is a very global industry. Anything you work on, it's going to involve people from different cultures, and communication and understanding each other's accent is a very, very crucial part of it. Like very recently, until I think last year, I was quite involved in working with Europeans. I could understand different accents very easily. And it goes the other way around too. They have to understand my accent too. It's not a fight. It's like both of us are trying to collaborate. And recently I realized that there are some UK accents that I'm not so familiar with. And I was trying to work with a person. We were having a huge accent issue, and both of us apologized for it, because the work that person does, I'm really, really inspired by it, is much more experienced than me. And if I cannot communicate with that person well. It's just not right. So I immediately went and switched on a British show, which turned out to be really good, by the way. But that's what it makes things so much easier. So it's not just about uh, the kind of technical skill that I'm going for. There are so many other soft skills that I'm gaining too. And I don't think there's anything better than working with people from other cultures. It's a whole different and fulfilling kind of experience. So being a communicator, you said that, I'm really happy to hear it. Now you're also working in commercial company right now. How has that been from academia to this?
Yeah, so yeah, my path has been really interesting. I worked in academia. I led communications education at a university. Then I went to the space agency, did a few years there, and then last year, I think I was like, oh, the only place I have, like, the only field I feel like within the space domain I have not worked is industry. And so this really neat opportunity came at, the company's name is Obruta Space Solutions, to work as an operations and project manager. And I said, oh, I've done project management, I've done operations. And I think what I really like is the team that I get to work with, they're young folks, very passionate, just like me, enthusiastic about wanting to have ideas, creative ideas, and then implement them. And that's the kind of passion that I look for when I work with people, is that similar, frequency. And I found that this is the team that is doing that. And the mission that we're working on is, rendezvous proximity operations and docking, which is what we talked about earlier, which is what the new next thing is in space, right? That's what we're talking about, is all of these satellites that are in space that are, either, some faults, something happened and it's faulty, cannot be operating, you need it to fix it, or else you're not going to be able to use it. And so it's thinking about sustainability, but at the same time, it's part of space. So there's so many things that went, in that process as I was thinking about what the company is doing, what my contributions could be. As someone who has experience from academia and the government. So, it was really the right space. And so I think an interesting diversion from what I was doing before. And I wouldn't call it diversion, because I do envision myself, having this being my path forward.
Rendezvous and docking is a dream of an engineer. It has so many applications.
Yeah.
It could be used in orbit refueling that a lot of people are talking about. OTVs are being built on that. And then docking is how space station is operating, literally, how it is living. And then if we are going to go for moon base or even to Mars, wherever, docking is one that complex. I remember those old space movies where they would show Gemini astronauts trying to drop. Oh my God, seeing that on the screen versus when you start to learn how it is done.
Yeah.
Do you really think that the ability to learn different things and also like translate your skills, it has something to do with that you are an artist by yourself?
I think so. Communicating is an art, I would say. I don't think I was born with that talent at all. It's a talent, like I said, is developed. I am the only scientist on the team right now in my company, right? Someone with a science background. But it also, I think, one of the things to think about, no matter where you are in space field, whether you're an engineer or scientist, like you mentioned before, soft skills and other skills are very important. So seeing something, my observational skills help me in my art. And it's the other way around as well, right? Like when I'm doing my art, I become more observational, whether it's like the color of the leaves or the color of the sky, like those small things translate into your work too, because now you're looking at data, or, you're looking at a project that is happening, you can envision things, you're observing a lot of the, what is going to happen, you're forecasting. So they're all transferable in so many ways. And so a lot of the people don't think about art being that, integrated into STEM. People always talk about STEM and not STEAM. But I have realized over the years that, if you're a scientist or engineer, you cannot communicate what you're doing what you're doing will not be useful to other people, even if it's people on the team. So then what is the point of you doing it? Right? Because not everyone on the team has the same background. So, if I'm a scientist and I'm trying to understand what an engineer is doing, they got to be able to explain me in non-engineering terms or terms that other people will understand. I could develop my vocabulary of engineering over time, or concepts that, I may have not studied as part of my education, but it also is on the person who developed it to be able to explain it, right? So it really is engaging other people in what you do. So if you're excited about wanting to share something you're doing, you got to think about talking to people who are not part of that field, right? And that's when you're sharing something that they may not know about, something that you're passionate about that they might get interested in. So I think the art influences my everyday work and my science and everything else I do, and it's the other way around too. So it's really the mix that makes me what I do on an everyday basis.
I can't tell you how much value there is. There is so much to learn from what you just said. The communication helps even when you're working in just a company.
Yeah.
It's like 5 people in a startup. This is why sometimes founders and investors look for people with different kind of skills. But there's also one aspect, like a lot of people are here, they want to become communicators, but social media is one of the primary modes of communication for them. They just do not have time. So you are doing everything, seems very flawlessly. So how are you managing? I mean, you are doing a job that requires your full concentration. On top of that, you're living your own life. On top of that, you're creating for socials. How do you manage?
Not very well. There are ebbs and flow for things, sometimes there are external deadlines that really help push me to do things. A good example is a couple of weeks ago, like I said before, I did an art, booth at a local festival, and that pushed me to like finish my pieces and get everything ready and like, have a collection. I didn't have that before. So, putting yourself into places where you're like, oh, I have a deadline, I need to do this, really helps you focus on that. The other thing is, I try and like find things that are exciting enough for me to talk about, and not always be, I'm not one of those traditional folks who's online all the time. I don't talk about every possible topic, things like that. When Artemis was going on, I was so excited. I was talking about it all the time. Now I'm not as active, right? So I kind of balance it that way. I also feel like more recently I've been more into kind of my health, making sure I'm getting exercise and all of that. And so it's really pushing myself to do things. And so it may mean that sometimes I may not be doing a lot of art. Sometimes I may not be doing a lot of, my science communication or astrophotography. All of this will like come and go as it is. Obviously my 9 to 5 stays 9 to 5. That happens. And I've become very good at maintaining work-life balance as well, which is something what I didn't have before, and I realized it impacted my health a lot. And so I've in the recent years become more aware of like when I need to put in overtime, when I don't need to put in overtime, when can I get a leeway to just be able to do my regular 9 to 5. So I think it's a lot of mental gymnastics that I have to do. Is like, what am I going to do this weekend? How am I going to spend this weekend? And then just be very thoughtful on how I do it.
I'm glad to hear that. Only all of these wonderful things that you're doing will only happen if you stay healthy. So I do have a bonus question, surprise question for you. But before that, I would like to know what your advice would be for any student. I'm asking this specifically for astrophysics because it is one of those most scariest things that a lot of people drop off from. So what would be your advice?
I think if you're passionate about it, ask the right questions and find the right people. Move away from memorizing and move into understanding. And you may not understand all the concepts all the time, and that's okay. This is why you have people from different fields. So if you think, I resonated more with planetary and, stellar astronomy more than anything else, I gravitated towards that, worked towards it. So find what you're passionate about, find, how you actually learn and understand things, and then use that to actually be able to go in the field that you want, is what my advice for folks who want to do astrophysics in particular.
That's so beautiful. If you just remember this, that you don't need to understand everything all the time. That's really cute. That's why scientists are scientists, like they're exploring all the time. I see Nobel Prize pages always posting these quotes from scientists saying that I was wrong half of the time. I mean, come on, that's the beauty of it.
Yeah.
But now, Parshati, before I let you go, I have to ask you this. What is your favorite Gujarati dish?
Oh, this is a hard one. I think dokra, white dokra, is my favorite one. I mean, oh my God. Okay, hold on. I feel like I'm doing bad to undiyu, because undiyu is also like one of those things that like brings me home when I make it here or have it here. I'm just like, brings me, back to my days. And I would say undiyu. Second to dokra is gonna second. It's like undiyu.
All right. We'll take that. You can pick and choose and change your answer later. But thank you. Thanks so much. It has been so wonderful talking to you. There's lots of things to learn from you. There's so many nuances to things you said. Is there any last words you would like to share?
I think I'll just say, be curious about the night sky and the world around you. We're losing our night skies, like, from what we even had 10 years ago, and it will likely probably just get worse. So just experience what we have right now, admire the beauty, try to learn about our place in the universe, even if it doesn't mean that you need to be an astrophysicist, you need to go to get education. There are tons of books and thanks to social media, tons of people to follow and learn from as well. So continue to be curious is what I'm going to leave you with.
Thank you so much to everyone watching. I'm going to share the details of socials from Parshati Patel. Please go follow. She does a lot of exemplary educational work, and you also get to see her art. So there's a lot to learn from, and please stay subscribed to this channel. I took a break for 6 months from this podcast. Like you said, I just needed to get to some deadlines, but I'm back with a lot more episodes. Dr. Patel, thanks so much for helping me relaunch this podcast.
Thank you for having me. I had a fun conversation, and I hope, people get excited and interested in the field, which is so exciting.